Optimization of the sintering process of electroerosive tungsten-free carbide particles. Introduction. Currently, sintered carbide alloys are widely used in various industries, in particular, in the production of construction machinery and equipment. However, the problem of saving such an expensive material as tungsten is acute. In order to save scarce tungsten, tungsten-free hard alloys based on carbides, as well as carbonanitrides of transition metals, primarily titanium, have been developed. The relevance of recycling this alloy is associated with the presence of expensive components in its composition. One of the most promising and not industrially used methods for grinding any conductive material, regardless of its hardness and other properties, is the method of electrical discharge dispersion. To predict high physical and mechanical properties of sintered products, from electroerosive charge, electroerosive particles of tungsten-free hard alloys, it is necessary to optimize sintering modes by setting up a full factorial experiment. Materials and methods. To carry out the planned research, tungsten-free hard alloy waste was selected. An oxygen-containing working fluid, distilled water, was chosen as the working fluid. For waste dispersion and installation, protected by RF patent number 24.49.85 was used. Consolidation of electroerosive particles was carried out using the thermal technology spark plasma sintering system model 25-10 on figure 1. Determination of the optimal parameters. Optimization of the process of consolidation of a new alloy based on the micro-hardness of sintered samples was carried out by setting up a full factorial experiment of type 23. To assess the influence of these factors and mathematically describe the process of producing tungsten-free hard alloy by spark plasma sintering of particles, a first-order model of the form represented by equation 1 was used, in which x1, x2, x3 are factors, temperature, pressure, and holding time. Accordingly, G is the value under steady micro-hardness. The levels and variation intervals presented in Table 1 were selected, and a planning matrix was compiled for the experiment conducted with the charge on Figure 2. According to the calculations carried out, a regression equation was obtained that simulates a full factorial experiment for sintering a charge obtained in distilled water. All coefficients of the equation modeling a full factorial experiment in distilled water, except B12, B13, B23, B1-3, turned out to be statistically significant. After excluding statistically insignificant coefficients, the regression equation takes the form. The resulting equations were used to climb the response surface steeply. The steep ascent of the charge obtained in water began from the 0-point main levels. According to a series of experiments, the limiting values of the optimization parameter Y micro-hardness were determined, which were, for samples obtained from particles dispersed in water 14, 15, 16 HV at temperature 1200 degrees Celsius, pressure 40 MPa and holding time 5 minutes. Testing the hardness of samples on the surface and across the cross-section was carried out using an automatic micro-hardness analysis system DM8. Using the micro-Vickers method with an indenter load of 50 gram, using 10 indentations with a free choice of the injection site in accordance with Gauss measurement of micro-hardness by indentation diamond tips. The indenter loading time was 15 seconds. Results and discussion. The results of studying the micro-hardness of samples of a new tungsten-free hard alloy obtained by spark plasma sintering are presented in the Table 3. It was experimentally established that the micro-hardness of sintered samples using the spark plasma sintering method from particles dispersed by electroerosion obtained in distilled water 14-15 HV. Conclusion. The first, the optimal parameters for the process of producing a tungsten-free hard alloy by spark plasma sintering of particles were determined based on the micro-hardness of sintered samples by conducting a full factorial experiment of type 23. The operating parameters of the spark plasma sintering installation were selected as factors, temperature, pressure, and holding time. The optimal operating parameters of the installation were determined for electroerosive material previously obtained from TFHA waste in an oxygen-containing environment, distilled water. The second, according to a series of experiments, the limiting values of the optimization parameter were determined which were for samples obtained from particles dispersed in distilled water 1415 HV, which is 16% higher compared to the original alloy, at temperature 1200 degrees Celsius, pressure 40 MPa, and holding time 5 minutes. Acknowledgements. The study was supported by the Russian Science Foundation grant number 24 29 0 31 and 6. Thank you for your attention.